In this lesson, we'll talk about taking the derivatives and integrals of exponential functions. We just did this with the natural log functions in the last two examples, and in this lesson we're going to do it for the exponential functions. Since you guys did inverse functions in college algebra, we'll spend more time working on the exponential functions and just remind you of the basic definition of inverses, what they mean, and a couple of their properties. Basically, what an inverse is it's a function that undoes a other function. G of x would undo f of x if doing the inverse and the original function gives you back x. And vice versa. If you do the original function and then the inverse, you just get x. We often use the notation f inverse of x. So a lot of what we're going to use for these in this course is simply this is an inverse when we define it. We'll define some functions as inverses of others, so we should know the basic ideas of what they are. Properties. If g is an inverse of f, then f is an inverse of g. They're inverses of each other. The domain and range of the function and the inverse get swapped, so the domain of the inverse is the range of the function. The range of the inverse is the domain of the function. Function does not always have an inverse. It only has an inverse when you get exactly one input for each output. And when it's true, you get a unique inverse. This is a property we call one-to-one, and it's the equivalent to the horizontal line test. If a function passes the horizontal line test, it has an inverse. One more thing to mention is that this -1 has nothing to do with exponents. It means inverse. -1 is an inverse. Every time you see it, you think of inverse. We won't really use that in this lesson, but it's going to come up in the inverse trig functions also. With this idea of inverses, we define the natural logarithm function as the inverse of the natural exponential function. So take the function y equals e to the x and take its inverse, and that's how we will formally define the natural log of x. With that said, if you have y equals the natural log of x, because it's an inverse of e to the x, you could say then x would equal e to the y. With that said, there's a few properties that come out of logarithms. First off, the natural log of e to the x, again these two are inverses, so they would cancel each other out and just leave x. E to the natural log of x would also cancel itself out and just leave x. And then there's a few properties of logarithms that come out of just working through the details of how the exponential function and the logarithmic function work together. You'll discover these four properties. The natural log of 1 is equal to 0. If you take the natural log of a product, you get the sum of the natural logs. The natural log of a quotient would be a difference of natural logs. And if you take the natural log of something raised to a power, you can bring the power to the front. And all of these are really helpful properties. Let's find the derivative of natural log of x. We're going to discover that it's equal to 1 over x, and this is how we'll prove it. Let's let y equal the natural log of x, and I'm interested in discovering y prime. So keep in mind that if you have y equals natural log of x, in the last slide it said x is equal to e to the y. So just reversing things, I'm going to say e to the y equals x. That's because the natural log and the e function are inverses. Now while this will look a little bit strange, I'm going to take the derivative with respect to x. Keep in mind y is a function of x, it's actually the natural log of x. But if I look at e to the y, I'm thinking e to some power. The derivative of e to the y is going to be e to the y times the derivative of that exponent, y prime. So that just used the chain rule. Now this is a little bit of a strange method. This is called implicit differentiation, and we'll study it a little bit more later. On the right side of the equation, the derivative of x is just 1. And then let's divide both sides by e to the y, and that will give us that y prime is equal to 1 over e to the y. But remember, we had something to do with e to the y. E to the y was just x. See it right here. So I get that y prime is equal to 1 over x as desired. Let's focus on finding some derivatives with our new rule. Remember, our new rule is that the natural log of x has derivative 1 over x. But that doesn't mean that we can just say it's 1 over x for any of them. We can couple it with other rules. We have the chain rule, the product rule, and the quotient rule. This first one uses the chain rule. We've got like a natural log of u here, so the derivative is 1 over u times the derivative of the inside, your u. So we get 1 over x squared plus 1 times the derivative of the inside is 2x. So we get 2x over x squared plus 1 as our final answer for this derivative. Next example. This one requires the product rule. We've got x times the natural log of x. You got a first term and a second term. Let's use our product rule. The product rule says you take the derivative of the first times the second plus the derivative of the second times the first. I just wrote all that out. I didn't take any derivatives yet. Now let's calculate the derivatives. I get 1 times the natural log of x. And remember, the derivative of natural log of x is 1 over x times x. So what happens is I get the natural log of x, and in this term the x's cancel, and I just get plus 1. This time I've got the natural log of x function inside of a fourth power. Now when that happens, it is a chain rule, but the inside is the natural log of x this time, whereas before it was the inside of the log. So I think of this like u to the fourth. U to the fourth would be 4u cubed when I take the derivative of it. But u to the fourth becomes 4u cubed times the derivative of your u inside. So I get 4 times natural log of x cubed, and the derivative of natural log of x is 1 over x. So if you want to rewrite that slightly, you could do it as 4 natural log of x cubed over x. The line right above is acceptable though. Now for this one, look at this monstrosity. That's a lot of stuff in there, and this would be a nightmare to take the derivative of just using the chain rule, because you'd have to use the product quotient and chain rules on the inside of the chain rule. It would be a mess. However, let's use our properties of logarithms. I've got the natural log of x plus the natural log of x squared plus 1 to the third minus the natural log of the square root of 3x squared plus 2. Just recall how the properties of logarithms work here. If it's in the numerator, it's positive. If it's in the denominator, it's negative. Whenever I took this apart, I really took the numerator, which was all of this, minus what's on the bottom, because a quotient becomes subtraction. And then the numerator can also be split, because a product becomes a sum. Let's do one more step to clean this up by bringing the powers in front. So I get 3 natural log of x squared plus 1. And just like what we did in the previous example, we've got a 1/2 natural log of 3x squared plus 2. Now we can take the derivative. L prime of x equals the derivative of natural log of x is 1 over x. The derivative of 3 natural log of x squared plus 1 is going to have a 3 in front. Then by the chain rule, natural log of u becomes 1 over u times the derivative of the inside. 1/2 in front for the next term. Same thing. 1 over 3x squared plus 2 times the derivative of 3x squared plus 2. 1 over u times the derivative of the inside. Remember, the 1 over u is strictly because I'm using natural log, and the derivative of natural log of u is 1 over u. I'm going to simplify this a little bit, but not a lot. See, we get 3 over x squared plus 1, and the derivative of x squared plus 1 is 2x. We could write this as 6x over x squared plus 1 if we had more space. And then we've got 1 over 6x squared plus 4, multiplying through by 2. And the derivative of 3x squared plus 2 is 6x. You could write this as 6x over 6x squared plus 4 if you wanted to, and you could even cancel out a common factor of 2. Either way, this will be my derivative. Now we've talked about the log, the natural log. We've talked about the natural exponential function, and we call this base e for both of these. However, exponential functions can certainly be used with things other than e. If a is not equal to 1, then we define the function a to the x by e to the natural log of a times x. So that's our official definition, but exactly what you are used to is what it means. If a equals 1, we just define 1 to the x to be 1. This definition, e to the natural log of a times x, will mainly be used for us to come up with a derivative rule involving any number to the x power. We can also talk about logarithms of bases besides just the natural logarithm. The official definition for this is that the log base a of x is going to equal the natural log of x over the natural log of a. That's our official definition, as long as a does not equal 1. We won't talk about a logarithm when a equals 1. This definition also has all the properties that apply to natural log, applies to logs of any base whatsoever. Here's the derivatives involving these functions. Here's our way to set this up. The derivative of a to the x, if we use the definition of this was e to the natural log of a times x. Now let's use the chain rule. Well, that's e to the natural log of a times x, it's like e to the u, times the derivative of the inside. And so this is just a to the x. And the derivative of the inside, the x goes away, and I get the natural log of a. Sure enough, the rule is natural log of a times a to the x, and that's correct. Next, the derivative with respect to x of log base a of x. Again, let's write out the definition. Log base a of x is defined to be natural log of x over natural log of a. We know that natural log of a is just a constant, so we can write it in front. And the derivative of natural log of x is 1 over x. But that's exactly what we have here. Just multiply straight across of any base. Let's do some problems with these. For this one, we need the chain rule. And so we're thinking 2 to the u, where u is x squared. The rule for 2 to the u would be natural log of 2 times 2 to the u times the derivative of your u, the inside. So we get natural log of 2 times 2 to the x squared, and the derivative of x squared is 2x. You could clean that up a little bit, but I'm not going to. G prime of x. We've got log base 3 of u. So the rule for log base 3 is 1 over natural log of 3 times u times the derivative of u, the inside. So we get 1 over natural log of 3 times cosine x, then times negative sine x. We'll leave it like that. Next one. This one, I'm going to think of it as square root of u. Then I've got a 4 to the x plus 4x. So we know the derivative of square root of u is 1 over 2 square root of u, our usual strategy, times the derivative of the inside. So we get 1 over 2 square root of 4 to the x plus 4x. And the inside is, well, the derivative of 4 to the x is natural log of 4 times 4 to the x. And the derivative of 4x is just 4. So there's our setup for this one.